What if our sun wasn't alone, but part of a cosmic family of 6 stars dancing together in space? We often think of our solar system as normal, but the universe loves to defy expectations. Imagine looking up at a sky with not 1, not 2, but 6 suns, some rising, some setting, some locked in an endless gravitational dance. It sounds like science fiction, but these extraordinary systems are real, and they hold secrets that are reshaping our understanding of the cosmos. Welcome to the bizarre and wonderful world of sextuple star systems. For centuries, astronomers believed that most stars, like our sun, lived solitary lives or had just 1 or 2 companions. But as our telescopes grew more powerful, we began to uncover systems that defied all expectations: complex families of 3, 4, and even 6 stars bound together by gravity. These aren't just random collections of stars, they are precision cosmic clocks with orbits so finely tuned that they challenge our very models of how star systems form and evolve. Some of these systems are so strange that they seem to break the rules of physics as we know them. In this video, we're going to explore 30 of the most astonishing discoveries about these incredible 6-star families. From gravitational puzzles that leave scientists scratching their heads to the tantalizing possibility of habitable zones where life could exist under multiple suns, these findings are rewriting the textbooks. You're about to embark on a journey into one of the most mysterious and awe-inspiring corners of our universe, a place where reality is stranger than fiction, and every discovery opens up new questions about the nature of space itself. So settle in and let's dive into the marvels of sextuple star systems. Our journey into these cosmic families begins close to home, relatively speaking, with one of the most recognizable patterns in the night sky, the constellation Gemini, the twins. For millennia, one of its brightest points of light, known as Castor, was admired as a single, brilliant star. Ancient astronomers charted it, navigators used it, and poets wrote about it, all under the assumption it was a solitary beacon. But as our technology advanced, the truth about Castor began to unravel in the most spectacular way. With the advent of powerful telescopes in the 19th century, astronomers made a shocking discovery. Castor wasn't 1 star, but 2. This binary pair, Castor A and B, was a revelation in itself. Yet the story was far from over. As spectroscopic techniques improved, allowing scientists to analyze the light from stars in incredible detail, they found that each of these 2 stars was itself not a single entity, but another binary pair. This meant Castor was actually a system of 4 stars, 2 pairs locked in a wide orbital dance. But the final, most astonishing layer of this cosmic onion was still to be peeled back. Further observations revealed a third, much dimmer binary star system, now called Castor C, gravitationally bound to the other 2 pairs from a great distance. After centuries of gazing at what appeared to be a single pinprick of light, we had to completely rewrite our understanding. Castor was in fact a sextuple star system, 3 separate binary pairs all waltzing around a common center of gravity in an intricate hierarchical ballet. This discovery was a profound lesson in cosmic humility. It demonstrated that even the most familiar objects in our sky can harbor unimaginable complexity, forcing us to question what other secrets the night sky might be keeping just out of sight. After the revelation of widely separated systems like Castor, you might assume that sextuple stars are all about maintaining a safe, spacious distance. But the cosmos always has a more extreme story to tell. Meet one of the most baffling configurations ever found, a system where stellar companionship is taken to a breathtakingly intimate level. In this particular family of 6 stars, 2 of the binary pairs are locked in an orbital embrace so tight that the entire dance could fit comfortably within the orbit of Mercury around our sun. Think about the scale for a moment. In our solar system, Mercury takes 88 days to complete its journey around the sun. In this distant system, two pairs of stars complete a full loop around each other in a matter of just a few Earth days. Their orbital periods are so brief that a human lifetime would witness thousands of these cosmic cycles. This proximity defies our basic intuition about gravity and chaos. With such immense masses whirling around each other at such close range, the gravitational forces at play are almost unimaginable. You would expect such a setup to be a recipe for disaster, a swift and violent end where stars either collide in a cataclysmic explosion or fling each other out into the void of interstellar space. Yet, against all odds, this system persists. It's a cosmic high-wire act that has apparently been stable for millions of years. This incredible stability is the central mystery that captivates astronomers. It suggests there are delicate, unknown mechanisms acting as gravitational referees, maintaining order in what should be pure chaos. Scientists theorize that these stars might be locked in precise orbital resonances, their gravitational pulls fine-tuned like perfectly timed pushes on a swing, keeping them in a stable rhythm. Alternatively, the star's orbits could be arranged in a specific, offset alignment that minimizes disruptive tidal forces, the same kind of forces that pull on our oceans, preventing them from transferring too much energy and causing the orbits to decay. Discovering a system like this is like finding a perfectly balanced spinning top that never wobbles. It shouldn't be possible according to our standard models, and yet there it is, spinning away in the depths of space, challenging us to understand the hidden rules of celestial mechanics. This staggering range of stellar personalities within a single family presents a profound cosmic puzzle. Conventional star formation theory suggests that stars born from the same collapsing cloud of gas and dust should be relatively similar in mass, like siblings sharing a common genetic heritage. The cloud fragments and each collapsing knot forms a star, with the available material in that immediate region determining its size. In most systems, this results in stars that are at least in the same general weight class. But in this system, it's as if a sumo wrestler, a professional athlete, and a newborn are all direct siblings from the same parents. Living in the same house, it fundamentally challenges our understanding of the family's history. The existence of such extreme mass variations points to a far more dynamic and chaotic nursery than we ever imagined. Astronomers are forced to consider that this system's birth cloud must have been incredibly turbulent and uneven, with pockets of extremely dense gas collapsing to form the behemoth blue giants right alongside regions of sparse material that could only muster faint red dwarfs. Another compelling theory suggests that perhaps this wasn't a single, calm collapse event, but a series of triggered formations. The immense radiation and powerful stellar winds blowing out from the first massive star to form could have compressed nearby gas, initiating a second wave of star creation, and then a third, each wave having less pristine material to work with, resulting in progressively smaller stars. It's a stellar assembly line where the product changes dramatically with each shift. This system forces us to ask whether our models of a quiet, isolated cloud gently giving birth to stars are too simplistic. The real universe appears to be a much rougher neighborhood where the formation of stars is a violent, competitive process, and the final family portrait can be wildly diverse. Understanding this bizarre mass distribution is key to unlocking the true, chaotic story of how stars are born, not in isolation, but within the complex gravitational webs of multi-stellar systems. If the idea of such wildly different stars sharing a home is baffling, consider the notion that these chaotic systems could also be nurturing planets. For a long time, astronomers held a firm belief: the complex, violent gravitational environment of a multi-star system would be a planetary demolition derby. The constant, shifting tugs from multiple stars would disrupt the gentle, delicate process of planet formation, scattering the primordial dust and gas before it could ever coalesce into a stable world. Any planet foolish enough to form would be flung into a wildly erratic orbit or ejected into the frozen depths of interstellar space entirely. This was considered a fundamental rule. But the universe, as it so often does, has handed us a remarkable exception. In one particularly astonishing sextuple system, observations have revealed the clear, telltale signature of vast, dense disks of dust and debris encircling not just one but several of the stars. These are not random clouds of junk. Their structure and composition are identical to the protoplanetary disks we see around young, single stars, the very cradles of planet birth. This discovery is akin to finding a perfectly arranged nursery with cribs and toys in the middle of a hurricane. The mere existence of these stable disks in such a chaotic gravitational field is a monumental puzzle. It suggests there must be protected, calm niches within the system, gravitational sweet spots where the competing pulls of the stars somehow cancel each other out, creating a temporary oasis of stability amidst the orbital storm. Now picture the conditions for any world that might form there. Your sun would not be a singular, constant beacon in the sky. Instead, you would experience a celestial dance of multiple suns of different colors and intensities, constantly rising and setting in a complex, unpredictable ballet. The gravitational forces tugging at your planet would change from moment to moment, potentially stretching its very structure. The climate would be a study in extremes, with temperatures swinging wildly as different stars took turns dominating the sky, bringing blistering heat from a blue giant followed by a dim, cool period under a red dwarf's faint glow. A year wouldn't be a simple orbit. It would be a chaotic, unpredictable path constantly being reshaped by its stellar parents. The fact that planet formation seems to be attempting this feat against such incredible odds forces a complete re-evaluation of what we consider a habitable zone. We can no longer simply draw a circle around a single star and declare that region life-friendly. We must now consider intricate, multi-dimensional zones of stability where gravity, light, and heat from several sources combine to create just the right conditions for liquid water and perhaps life to persist. Finding a planet in a system like this would be the ultimate testament to nature's perseverance, proving that even in the most tumultuous environments, the universe still finds a way to build a home. Just when we thought we understood the intricate dance of these 6 star families, we stumble upon a discovery so perplexing it threatens to upend the very foundations of physics itself. In several of these systems, astronomers have meticulously tracked the paths of the stars, mapping their orbits with incredible precision, only to find that their movements are subtly, yet undeniably, wrong. The stars are not quite where our most fundamental laws of gravity say they should be. It's a gravitational paradox playing out on a cosmic scale. For centuries, we've relied on Newton's laws of motion and universal gravitation to predict everything from the fall of an apple to the orbit of Neptune. When we needed even more precision, Einstein's theory of general relativity stepped in, perfectly explaining subtle anomalies like the slight wobble in Mercury's orbit. These frameworks are the bedrock of modern physics, tested and proven time and again. Yet, in these complex sextuple systems, the predictions fall short. The discrepancies are small. Perhaps a star is a few thousand kilometers off its expected position after a complete orbit. But in the precise world of astrophysics, even a tiny error is a screaming alarm bell that our understanding might be incomplete. This leaves scientists with a thrilling and frankly daunting set of possibilities to investigate. The first and most conservative explanation is that we are simply witnessing the unimaginable complexity of a 6-body gravitational problem. The mathematical equations for predicting the motion of just 3 bodies interacting through gravity are famously chaotic and unsolvable in a perfect closed form. For 6 stars, the problem is exponentially more difficult. We may be seeing emergent behaviors, unpredictable patterns that arise from the sheer number of interactions that our current simulations simply cannot replicate because we haven't yet found the right mathematical approach to model them. A more exotic possibility involves dark matter. This mysterious, invisible substance that makes up most of the matter in the universe is thought to form vast, diffuse halos around galaxies. But what if smaller, localized clumps of dark matter could be gravitationally bound within these star systems themselves? An unseen concentration of dark matter nestled among the stars could be exerting an additional gravitational tug, subtly pulling them off their predicted courses. Proving this would be monumental, offering a rare, close-up laboratory to study dark matter's influence. The most radical explanation of all is that these orbital anomalies are evidence of something even more profound, that our theory of gravity itself requires modification in certain extreme conditions. What if gravity operates slightly differently when faced with the specific, complex configurations found in these systems? It's a long shot, but investigating these cosmic irregularities could be the key that unlocks a deeper, more complete theory of how the universe truly works. A theory that has been hiding in plain sight, encoded in the errant paths of 6 dancing stars. This cosmic puzzle of misbehaving orbits is not the only rule being broken in these complex families. We now turn to a discovery that strikes at the very heart of how we believe star systems are born. For decades, a fundamental principle of astronomy has been that stars within a gravitationally bound group are siblings. They are born from the same parent cloud of gas and dust at approximately the same time, sharing a common origin story. It's a tidy, logical model that has held up remarkably well. But one particular sextuple system has thrown a massive wrench into this elegant idea, presenting us with a celestial family portrait where the members seem to be from completely different generations. In this system, astronomers can estimate the age of stars by studying their color, brightness, and stage of life. A massive, hot, blue-white star burns through its fuel in a frenzied rush, living a short and brilliant life of only a few million years. A smaller, cooler, red dwarf star is far more frugal, sipping its hydrogen fuel for trillions of years, essentially forever on a cosmic timescale. When we apply these clocks to this system, the result is baffling. One binary pair is composed of these brilliant, short-lived blue giant stars in the prime of their youth, perhaps only a few tens of millions of years old. Yet another pair in the same gravitational family are dim, cool red dwarfs that show all the signs of being ancient, perhaps several billion years old. The age gap between these stellar pairs is not a small difference of a few million years. It is a staggering chasm, as if a newborn infant and a millennia-old redwood tree were claiming to be twins. This age discrepancy is a profound mystery that challenges the core of stellar formation theory. If all 6 stars were born together from a single cloud, they should all be the same age. The fact that they are not forces astronomers to consider far more dramatic and dynamic origin stories. The leading hypothesis is stellar capture, the idea that these stars did not form together but were strangers that somehow found each other in the vastness of space. Perhaps this system began as 2 separate, older binary pairs drifting through the galaxy. Billions of years later, a much younger binary pair formed nearby, and through a complex gravitational interaction, maybe a close encounter or a gentle nudge from a passing star, they were all snared into a shared orbit. But the capture theory is incredibly difficult to prove. The space between stars is mostly empty, making such a precise multi-star capture event seem almost impossibly rare. It would require a perfect balance of speeds and trajectories to bind them together without tearing them apart or sending them flying away. This has led to other, even more speculative ideas. Could a star have undergone a peculiar, delayed formation? Perhaps the parent cloud that birthed the younger pair was itself triggered into collapse by the passage of the older system, making them distant gravitational cousins rather than direct siblings. Or could a catastrophic event like a supernova in a previously more massive system have ejected some stars and reset the evolutionary clock for others, creating the illusion of different ages? This single, strange family of stars forces us to question whether our quiet, isolated model of star formation is the whole story. It suggests that the universe might be a much more sociable and interactive place, where stars can adopt orphans and form blended families, creating the complex gravitational systems we see today through a history of chance encounters and cosmic luck. Just when we think we have mapped the grand orbital ballet of these 6 star systems, a new layer of mystery reveals itself in the most precise way imaginable, through the silent, rhythmic ticking of eclipses. In certain sextuple systems, astronomers have identified pairs of stars that orbit each other in such a perfectly edge-on alignment from our viewpoint that they regularly pass in front of one another, causing their combined light to periodically dim. These eclipses are the most reliable clocks in the cosmos, occurring with metronomic precision. By calculating the immense gravitational forces at play, scientists can predict the exact second one star should begin to obscure its partner, years or even decades in advance. But in these particular systems, the clocks are running slightly fast or slow. The eclipses are arriving a few seconds, or sometimes minutes, earlier or later than our most sophisticated models dictate they should. These are the eclipse timing variations, and while the discrepancy seems small in the world of astrophysics, it's a glaring red flag that something is very wrong with our picture of the system. This anomaly is a classic case of celestial detective work. The principle is simple yet powerful. If the eclipse of a binary pair is consistently early or late, it means something unseen is gently tugging on the pair, subtly speeding up or slowing down their orbital dance. The pattern of these timing delays and advances acts as a fingerprint, allowing astronomers to reverse engineer the source of the gravitational perturbation. In a system with 6 known stars, the first suspicion would be the gravitational influence of the other 4 members. But after accounting for every single one of them with painstaking accuracy, a residual timing signal often remains, a ghost in the machine, a gravitational signature with no visible source. This is where the search for the truly invisible begins. The precise nature of the timing variations points directly to the mass and orbit of the hidden object responsible. In several cases, the data suggests the culprit could be a brown dwarf, a failed star too massive to be a planet but not massive enough to ignite sustained hydrogen fusion in its core. These dark, Jupiter-like giants have long been theorized to be common throughout the galaxy, but they are incredibly difficult to spot directly because they emit almost no light. Here, their gravity betrays them. In other systems, the variations hint at something even more exciting: a Jupiter-sized planet or a whole family of them, orbiting one of the binary pairs and giving it a gentle gravitational nudge with every pass. The most thrilling possibility, however, is that these timing variations could be the first indirect evidence for an entire class of exotic, dark objects lurking within these systems. We are forced to ask, could we be detecting the gravitational influence of a rogue planet that was captured by the system, a primordial black hole left over from the Big Bang, or a dense knot of the mysterious dark matter we've been searching for? Each eclipse that occurs a few seconds off schedule is a message, a tiny piece of data in a cosmic puzzle that could lead us to discoveries far beyond what we set out to find. It demonstrates that even when we believe we have a complete inventory of a star system, the universe always has more secrets to reveal, hidden in the silent gaps between the ticks of a light-year-wide clock. But the gravitational dance of these stars is only half the story. There's another, more invisible force at work in these systems, one that weaves an intricate web of energy between the stars, sometimes across astonishing distances. We're talking about magnetism. In our solar system, the sun's magnetic field creates beautiful auroras on Earth and drives space weather, but it's a solo act. Now imagine that effect multiplied and intertwined across 6 different stars, each with its own powerful magnetic personality. In certain sextuple systems, astronomers have detected something truly extraordinary: complex, synchronized magnetic interactions that create stellar auroras and radiation storms on a scale that completely dwarfs anything we've ever witnessed. The sheer power of these magnetic displays is almost incomprehensible. Where Earth's auroras are gentle curtains of light caused by solar particles dancing with our atmosphere, the auroral events around these stars are likely cataclysmic. We're talking about planet-sized ribbons of energy, raging radiation storms that would sterilize any nearby world, and constant, high-energy particle beams shooting between the stars like cosmic lightning. These aren't just pretty lights, they are titanic releases of energy shaping the very environment of the entire system. The truly baffling part, the real mystery that has physicists scratching their heads, is how these magnetic fields appear to be synchronized. In one observed system, a flare erupts on a star in one binary pair, and almost immediately, a corresponding flare erupts on a star in a completely different pair located billions of kilometers away. It's as if the stars are communicating, or more precisely, as if their magnetic fields are somehow entangled, acting in concert across the void. This coordinated stellar activity suggests a form of magnetic communication or resonance that goes far beyond our current understanding of physics. Our best model for this behavior, magnetohydrodynamics, which describes how magnetic fields and conductive fluids like plasma interact, struggles to explain this kind of long-distance, instantaneous coordination. It would be like trying to explain how two tuning forks placed on opposite sides of a concert hall begin vibrating in perfect unison without any physical connection or sound waves between them. One theory is that the space between the stars isn't entirely empty. It could be filled with a thin, conductive plasma that acts as a medium, allowing magnetic signals to propagate. Another, more speculative idea is that we are seeing the effects of magnetic field lines themselves becoming directly connected, creating vast, invisible bridges of force through which energy can be transferred almost instantaneously. This magnetic symphony forces us to reconsider the very nature of stellar relationships. Stars in these complex systems aren't just gravitationally bound, they are electromagnetically coupled, their fates woven together by invisible lines of force. Understanding this bizarre phenomenon isn't just about adding a new chapter to astrophysics. It's about discovering a whole new language of stellar interaction, one written in the silent, powerful script of magnetic fields. Beyond the gravitational and magnetic oddities, we now encounter a mystery written in the very chemistry of these stars. When astronomers point their spectrographs at the light from these 6 star families, they break it down into a rainbow of colors, a spectral fingerprint that reveals the exact elements burning in each star's atmosphere. For most stars, this fingerprint is predictable. Older stars formed early in the universe's history show a purer composition, rich in hydrogen and helium but lacking heavier elements, which were forged later in the hearts of massive stars and scattered by supernova. Younger stars born from recycled gas are metal-rich, but in several sextuple systems, this cosmic rulebook has been tossed out the window. The chemical signatures are bizarrely out of place, showing concentrations of heavy elements like gold, platinum, and uranium that are wildly inconsistent with the star's estimated age or its location in the galaxy. It's the astronomical equivalent of finding a medieval knight wearing a digital watch. The components simply don't belong together. This chemical anomaly forces us to consider 2 revolutionary possibilities, each more fascinating than the last. The first centers on nucleosynthesis, the process by which stars create new elements. We understand the basics. Hydrogen fuses into helium, and in a star's final, violent stages, it can forge heavier elements through processes like the rapid neutron capture process, or R process, which requires an immense flood of neutrons. This is thought to occur primarily in cataclysmic events like supernova or neutron star mergers. But what if the unique, dynamic environment of a sextuple system is creating a new, unknown pathway for element creation? The intense gravitational squeezes and tidal forces as stars whip around each other at close range could potentially trigger unusual fusion reactions in their cores or on their surfaces, cooking up heavy elements in situ, right there in the stellar furnaces. This would be an entirely new channel for nucleosynthesis, one that doesn't require a supernova but is instead powered purely by the complex gravitational dance of multiple stars. The second, and perhaps even more plausible, explanation is an astronomical game of tag called mass transfer. In a simpler binary system, if one star swells into a red giant, it can spill its material onto its companion, altering the recipient star's chemical makeup. But applying this idea to a system with 6 stars adds layers of almost unimaginable complexity. Imagine a scenario where one star undergoes a transfer event with a partner, becoming enriched with unusual elements. Then, through an intricate series of gravitational interactions within the larger system, that chemically altered star could itself interact with a third star, passing on its strange composition. It could become a game of cosmic hot potato, where packets of chemically enriched material are tossed between stars across vast distances over millions of years. This would require a stability and precision in the orbits that we currently struggle to model, suggesting these systems can act as efficient factories for mixing and distributing elements in ways we never thought possible. The implications of this stellar alchemy stretch far beyond these individual systems. The heavy elements that make up our planets and indeed our very bodies were all forged in stars. If sextuple systems are indeed undiscovered factories for creating and dispersing these elements, then they may have played a far more significant role in seeding the galaxy with the building blocks of planets and life than we ever gave them credit for. Their strange chemistry isn't just a curiosity, it could be a vital clue to understanding our own cosmic origins. Just when we think we've mapped every possible orbit in these stellar families, we encounter a system that spins the entire narrative on its head, literally. In a configuration that seems to defy the very physics of its own creation, one sextuple system contains a binary pair that is flying in the wrong direction. While the majority of the stars orbit the system's common center of gravity in a prograde or forward direction, like all the planets in our solar system around the Sun, this one rebellious pair is moving in a retrograde orbit, circling backwards relative to everyone else. It's the cosmic equivalent of watching a car suddenly decide to drive the wrong way down a highway, weaving seamlessly through oncoming traffic without a collision. This isn't a minor orbital quirk, it's a fundamental violation of our standard model for how star systems are born. The principle it violates is one of the most basic in astrophysics, the conservation of angular momentum. Picture the massive cloud of gas and dust that collapses to form a star system. As it shrinks, it begins to spin faster, much like a figure skater pulling their arms in. This spin imparts a preferred direction of rotation to everything that forms from that cloud, every star, every disk, every potential planet. Everything should be spinning and orbiting in the same general direction, a family all moving together. A retrograde orbit within such a family is therefore an enormous paradox. It suggests that this binary pair did not inherit its motion from the shared parent cloud, but instead acquired it from somewhere else after the fact. So how does a pair of stars end up going the wrong way? Astronomers are investigating several thrilling possibilities, each more dramatic than the last. The first is a gravitational slingshot event of incredible violence. Imagine that in the system's wild youth, there was a close encounter with another star system passing by. The gravitational pull from this intruder could have acted like a cosmic brake and crank, forcefully reversing the orbit of one binary pair. While this is possible, the mechanics are incredibly precise. The encounter would need to be close enough to have a dramatic effect, but not so close that it completely dismembered the system or flung the stars away entirely. Another, even more exotic theory involves a phenomenon known as the Castor mechanism. This is a gravitational effect where the orbit of one body can be torqued and tilted by the persistent pull of a distant third body. Over immense stretches of time, this interaction can slowly flip an orbit all the way over, past a 90-degree angle until it is effectively rotating backwards. In a sextuple system with its multitude of gravitational influences, such a process is theoretically possible, but it requires a perfect and stable arrangement of stars to provide the consistent pulling force over millions of years. The most mind-bending explanation, however, is that this retrograde pair are not native to this system at all. They could be interstellar immigrants, a binary system that was born elsewhere in the galaxy and was later captured. If they were drifting through space and approached the system from the opposite direction, the complex gravitational dance of capture could have locked them into their current backwards orbit. This turns the entire concept of a stellar family on its head, suggesting that some of these systems are not families by birth, but by adoption, assembled through chance encounters in the galactic void. The presence of a retrograde orbit is a silent, spinning testament to a much more chaotic and interactive galactic environment than we ever imagined, where the paths of stars can be radically altered by encounters we are only beginning to understand. While the gravitational and chemical mysteries of these systems are profound, one of the most visually stunning enigmas involves the very heartbeat of the stars themselves. In the serene darkness of space, many stars pulse, rhythmically expanding and contracting like cosmic lungs. These are variable stars, and their predictable changes in brightness are a window into their internal structure, driven by complex processes in their cores. Normally, each variable star has its own unique, independent rhythm. But in at least one known sextuple system, astronomers have observed something that should be impossible: multiple variable stars separated by trillions of kilometers, pulsating in perfect, synchronized harmony. It's as if you had 6 different orchestras spread across a continent, all playing the same symphony without a conductor and without missing a single beat. This synchronization is a deep mystery because the mechanism behind a star's pulse is an internal affair. The rhythm is set by a delicate balance between the outward pressure of radiation and the inward crush of gravity within the star's own structure. For 2 such stars to sync up, something must be communicating between their cores, influencing this most fundamental of processes across the void. The vast distances involved rule out any direct physical connection. These stars are much too far apart for their surfaces to touch or for any material to flow between them. This leaves scientists with 2 primary and equally fascinating suspects: gravity and light. The gravitational explanation pushes our understanding of this force to its limits. We know gravity binds the stars in their orbits, but could its subtle, rhythmic tugs be fine enough to act as a metronome? As the stars orbit, the gravitational pull each one feels from the others changes minutely. The theory is that these tiny, periodic tidal forces could be gently squeezing and relaxing the stars' outer layers, literally pumping them in time with the orbital period. For this to work, the natural internal rhythm of the stars would have to be almost perfectly matched to the orbital rhythm, creating a resonance that locks their pulses together. It's an incredibly delicate process, like using the gentle, rhythmic vibration from a passing train to synchronize the pendulums of clocks in distant buildings. The alternative theory is even more extraordinary: communication by light. We often think of light simply as illumination, but it also carries momentum and exerts a tiny amount of pressure. The idea is that the incredible luminous output from the hottest, brightest stars in the system could be bathing the others in a powerful, rhythmic flood of radiation. The pressure from this light could be enough to push on the atmospheres of the pulsating stars, either damping their natural rhythm or driving it, effectively forcing them into sync. This would be a form of radiative entrainment where the sheer brilliance of one star dictates the heartbeat of another. The pulses would then travel across the system at the speed of light, creating a near instantaneous connection that gravity cannot match. This inexplicable synchronicity does more than just present a puzzle. It offers a revolutionary new tool for astronomy. These synchronized pulses act like a natural interferometer, a network of cosmic clocks that allows scientists to measure distances and masses within the system with unprecedented precision. By studying the minuscule time delays in the pulses, they can triangulate positions and track gravitational influences with a level of accuracy that was previously unimaginable. The stars themselves become partners in the observation, their linked heartbeats revealing the hidden architecture of their family in a way that passive light alone never could. This bizarre phenomenon transforms the entire system from a subject of study into an active participant, offering up its secrets through a silent, synchronized song of light and gravity. The existence of planets forming in these chaotic environments is mind-bending, but it hinges on one absolutely critical requirement: the survival of the raw material itself. Before any world can coalesce, there must be a stable reservoir of gas and dust, a circumstellar disk spinning calmly around a young star, serving as a planetary nursery. In the violent gravitational turmoil of a sextuple system, the very idea of such a delicate structure persisting seems laughable. The competing tugs from 5 other stars should shred these disks, scattering their material into the void before a single planetesimal can form. This was the unshakable assumption, but once again the universe has delivered a staggering surprise, a system where not one, but multiple circumstellar disks are thriving, each one orbiting its host star within a binary pair, utterly defiant of the gravitational chaos surrounding them. The discovery of these intact disks is akin to finding a collection of fine china, sets miraculously unbroken in the middle of a continuous earthquake. These are not the massive, shared disks that can sometimes encircle wide binary stars. These are individual, well-defined disks, each one tightly bound to its own star within a close binary partnership. Their survival presents a monumental puzzle. The gravitational perturbations from the other stars in the system should be constantly kneading and twisting these disks, injecting energy that would heat them up, disrupt their neat circular orbits, and ultimately tear them apart. The fact that they haven't suggests the presence of hidden, localized zones of stability, gravitational safe rooms where the disruptive forces are mysteriously cancelled out. Astronomers are racing to understand the physics behind this incredible preservation. The leading theory points to the specific architecture of the system itself. If the orbits of the binary pairs are aligned in a particular way, their gravitational influences might create what are known as Lagrange points, stable regions where the pull of gravity from multiple bodies balances perfectly. It's possible that these circumstellar disks are nestled within such a point, effectively sheltered from the storm. Another compelling idea is that the disks are themselves stabilized by the very star they orbit. In a close binary, the gravitational pull from the partner star could actually shepherd the disk, confining it to a tight region and preventing it from spreading out into a more vulnerable state. It's a form of gravitational guardianship where one potential threat becomes the very mechanism of defense. The implications of this discovery ripple far beyond this one system. It forces a complete rewrite of our models for planet formation. We can no longer assume that multi-star systems are automatic dead zones for planet birth. Instead, we must now look for these niches of stability, these gravitational eddies where the chaos momentarily stills and the quiet, delicate work of building planets can begin. It suggests that the universe is far more inventive and protective of its potential than we ever dreamed, creating safe harbors in the most unimaginably turbulent seas. The continued existence of these multiple disks isn't just an oddity. It's a beacon of hope, indicating that even in the most extreme environments, the fundamental processes of creation find a way to endure. While the synchronized pulses and protected disks reveal a system's hidden rhythms, another discovery points to a far more violent and energetic side of these stellar families. In the high-energy regime of the electromagnetic spectrum, where X-rays paint a picture of the universe's most extreme events, several sextuple systems are shining with an unexpected and ferocious intensity. These aren't the steady, predictable X-rays of a lone star's corona. They are powerful, fluctuating bursts that come and go without any clear pattern, and their sheer strength is completely out of proportion to the types of stars producing them. It's like hearing the occasional, deafening roar of a jet engine coming from a quiet suburban neighborhood. The source of the power is entirely out of place and demands an explanation. This intense and variable X-ray signal is a major puzzle because the usual suspects don't add up. For single stars, strong X-ray emissions typically come from two sources: the incredibly hot, magnetically heated outer atmosphere, or the corona, which is more active in younger, faster spinning stars, or from material accreting onto a dense remnant like a white dwarf or neutron star, releasing a torrent of X-rays as it falls. But in these systems, the stars themselves often don't fit the profile. They might be older, common stars that should have relatively quiet coronas, and there's no clear evidence of any dense stellar remnants in the right position to be the culprit. The energy output is simply too great, and its variability too erratic to be explained by the textbook models. This forces astronomers to consider that the very complexity of the system, the fact that there are 6 gravitationally intertwined stars, is generating entirely new, high-energy phenomena that we've never witnessed before. One leading theory is that we are seeing the effects of colossal magnetic reconnection events, but on a scale that dwarfs anything our sun can produce. A solar flare is caused when the sun's magnetic field lines become tangled, snap, and reconnect, releasing a tremendous amount of energy. Now, imagine that process not happening within a single star's magnetic field, but between the magnetic fields of 2 or more different stars. As these binary pairs swing through their orbits, the magnetospheres of their component stars could be periodically brushing against each other or even becoming temporarily connected. When these vast, separate magnetic structures interact, the resulting reconnection event would be catastrophic, unleashing a storm of high-energy particles and X-rays that would make a typical solar flare look like a mere spark. This would be interstellar, not just intrastellar, magnetism, a previously unimagined way for stars to exchange energy violently across space. An even more dramatic possibility involves a novel form of long-distance stellar collision. We typically think of collisions as 2 stars physically smashing into each other, but in the near-perfect vacuum of space, even a near miss can be spectacularly violent. The intense, focused gravitational pull of 6 stars could be slingshotting vast clouds of ionized gas and plasma at incredible speeds between the stellar members. These aren't collisions of solid bodies, but rather high-velocity impacts between streams of superheated material. When a cloud of plasma ejected from one star rams at a significant fraction of the speed of light into the magnetosphere or stellar wind of another star, the shock wave would generate a brilliant flash of X-rays, a temporary but incredibly powerful beacon signaling a collision that occurred across billions of kilometers. A third fascinating hypothesis involves the system's interaction with its environment. Space is not entirely empty. It is filled with a thin interstellar medium-ism, a diffuse soup of gas and dust. The complex gravitational field of a sextuple system could act like a series of giant lenses, focusing and concentrating this tenuous flow of interstellar material from different directions. As this funneled stream of gas is pulled in and accelerated by the star's gravity, it could be compressed and heated to millions of degrees upon impact with a stellar wind or circumstellar disk, producing the intense and variable X-ray emissions we detect. In this scenario, the system is essentially using its own gravity to gather fuel from a vast volume of space and ignite it in a continuous, chaotic series of high-energy explosions. Each of these theories pushes the boundaries of known physics, suggesting that when you pack 6 stars into a single gravitational system, you create a laboratory for extreme and previously unseen cosmic events. This incredible persistence, lasting not just millions but billions of years, presents one of the most profound mysteries in all of astrophysics, the hierarchical stability paradox. According to everything we know about gravitational dynamics, a system with 6 massive bodies should be a recipe for cosmic chaos. The mathematical equations that describe the motion of just 3 gravitationally bound objects are famously unsolvable in a perfect, predictable way. Their behavior is inherently chaotic, meaning even the tiniest initial mismeasurement leads to a completely different outcome over time. For a system with 6 stars, this chaotic nature should be amplified to an extreme degree. The gravitational pulls from so many massive objects should constantly perturb each other's orbits, transferring energy, creating instabilities, and ultimately leading to a dramatic breakdown. One pair should be ejected into deep space, or 2 stars should collide in a cataclysmic explosion, or the entire delicate arrangement should simply fly apart. The very existence of ancient sextuple systems that have avoided this fate for longer than our planet has existed is a paradox that strikes at the heart of celestial mechanics. So how do these systems cheat gravity? The leading theory points to a concept known as hierarchical stability. Instead of all 6 stars chaotically interacting with each other equally, they arrange themselves in a very specific nested order. Think of it not as a free-for-all mosh pit, but as a meticulously organized series of concentric dances. At the smallest scale, you have the tightest binary pairs with 2 stars orbiting each other incredibly closely. This pair then orbits with another binary pair at a much wider separation, forming a stable quadruple system. Finally, that entire quadruple system engages in a slow, grand dance with a third, even more distant binary pair. The key to stability is the vast difference in these orbital scales. The gravitational bond within each tight binary is so strong that it effectively acts as a single, consolidated mass when interacting with the other pairs from a distance. This dramatically simplifies the chaotic 6-body problem into a much more stable 3-body problem, where the 3 bodies are actually these consolidated binary pairs. The system protects itself by keeping its complex interactions local and its wider interactions simple. But hierarchy alone isn't the full answer. For this structure to survive for eons, the orbits likely need to be locked into precise gravitational resonances. This is where the orbital periods of the different pairs exist in a perfect integer ratio, like 2 gears meshing in a clock. For example, for every 1 orbit the wide outer pair completes, the inner quadruple system might complete exactly 4 orbits. These resonances act as a stabilizing mechanism, providing periodic, predictable gravitational nudges that actually reinforce the orbits rather than disrupt them. It's the difference between pushing a child on a swing at random, chaotic intervals, which would make them wobble and fall, versus pushing them at the exact peak of their arc every single time, which builds a smooth, stable rhythm. These ancient systems appear to have found that perfect cosmic rhythm. This incredible natural fine-tuning suggests that while chaos is a fundamental part of gravitational physics, stability is not an accident. It is an emergent property that complex systems can find and lock into. The existence of these billion-year-old sextuple systems implies there are islands of stability within the sea of gravitational chaos, specific configurations that are somehow self-reinforcing and incredibly resilient. Unlocking the secret of their longevity isn't just about understanding a few strange star systems. It's about searching for the fundamental principles of order that can arise from complexity. Principles that might govern everything from the formation of planetary systems to the largest structures in the entire universe. Just when we think we've catalogued every possible anomaly in these systems, from their synchronized pulses to their rebellious orbits, we encounter a mystery that strikes at the very spin of the stars themselves. In the vast majority of stars, rotation speed is a reliable clock. a young star spins rapidly, a product of the angular momentum from its birth cloud. Over billions of years, that spin gradually slows down through a process called magnetic braking, where the star's magnetic field interacts with its own stellar wind, acting like a cosmic drag chute. In simpler systems, this process is predictable, but in certain sextuple families, this clock is completely broken. Astronomers find stars that are spinning at velocities that make no sense whatsoever for their age or mass. Some ancient, massive stars are whirling around at a frantic pace, as if they were reckless teenagers, while other younger, smaller stars are rotating surprisingly slowly, acting like old souls before their time. It's a stellar spin paradox that defies all expectations. The root of this mystery lies in the complex web of interactions that simply cannot occur around a single, isolated star. For a star in a sextuple system, its rotation is not solely governed by its own internal processes. It is constantly being tugged, braked, and accelerated by its 5 siblings. The primary mechanism for this is tidal locking, a phenomenon we see in our own solar system where the moon's rotation has been synced to its orbit around Earth, always showing us the same face. In a tight binary pair within a sextuple system, this same process can force 2 stars to become tidally locked to each other, their rotations perfectly synchronized with their orbital period. This can dramatically slow down a star that should be spinning freely, but the story gets far more complex when you add 4 more gravitational players into the mix. The gravitational influence from the other, more distant pairs in the system can act as a persistent spoiler, preventing stars from ever achieving a perfect tidal lock. Instead of a steady, slow rotation, a star might be caught in a perpetual gravitational tug-of-war. One binary pair pulls to speed it up, another exerts a tidal force to slow it down, resulting in a strange, intermediate spin rate that matches no known model. It's as if the star is being simultaneously pulled in multiple directions by invisible strings, never finding a stable rhythm. This constant gravitational kneading can also transfer angular momentum across the system in bizarre ways. Imagine a figure skater pulling their arms in to spin faster. In a sextuple system, the gravitational interactions can act like a cosmic version of this, stealing spin from one star and transferring it to another across vast distances through the intricate choreography of their orbits. A massive star might have its rotation sapped, slowing it down prematurely, while that stolen energy is transferred to a smaller companion, whipping it into a dizzying, unexpected frenzy. Furthermore, the powerful magnetic fields we discussed earlier play a crucial and confusing role. Magnetic braking, the process that normally slows a star's rotation, could be amplified or nullified by the system's environment. If a star is bathed in the intense magnetic field of a more powerful neighbor, that external field could enhance the braking effect, slowing the star down much faster than if it were alone. Conversely, the violent gravitational interactions might be churning the star's interior, rejuvenating its internal dynamo and generating a stronger magnetic field that actually locks in its fast rotation, fighting against the forces that would normally slow it down. These strangely spinning stars are more than just a curiosity. They are live demonstrations of angular momentum transfer on a grand scale. By studying them, we are essentially watching the universe play with its own conservation laws, shifting spin and energy between stars like a celestial game of hot potato. This forces us to rewrite the chapter on stellar adolescence and aging, proving that for a star, your family doesn't just influence your life, it dictates how you turn. The warmth we feel from our sun is a familiar and steady constant, but for the inhabitants of a world in a sextuple system, the very concept of climate would be redefined on an almost unimaginable scale. Unlike the predictable seasonal shifts on Earth governed by a tidy tilt and a single star, the climate on a planet in a 6-star family would be a chaotic symphony of extremes, dictated by the ever-changing cast of suns in its sky. Each star, with its unique color, temperature, and distance, would contribute its own voice to this cacophony of heat and light, creating conditions that swing from one profound extreme to another with a rhythm that might be impossible to forecast over the long term. The sheer number of gravitational masters would yank the planet's orbit into a complex, potentially unstable path, meaning the planet's distance from each star is in a constant state of flux. One moment, it could be drifting through a relatively cool period, basking in the gentle glow of a distant red dwarf. The next, its orbit might bring it swinging perilously close to a brilliant blue giant, flooding the world with intense ultraviolet radiation and scorching heat that would boil away oceans and strip atmospheres. The length of a day, a year, and even the very definition of seasons would lose all meaning, replaced by a stochastic calendar of stellar proximities and eclipses. The potential for a stable, life-friendly environment in such a maelstrom seems vanishingly small, yet it's a possibility that astronomers can no longer completely rule out. The key lies in the concept of a shifting, multi-dimensional habitable zone. Around a single star, the habitable zone is a relatively narrow shell where temperatures are just right for liquid water to exist on a planet's surface. In a sextuple system, this zone becomes a fantastically complex and dynamic volume of space. It's not a single region, but a series of overlapping and interacting spheres of influence from each star, their boundaries constantly moving as the stars dance through their orbits. A planet might only experience conditions suitable for life when it occupies a specific point where the combined energy from, say, two cooler stars perfectly balances the absence of a hotter one, or during a brief golden era when all the gravitational forces align to lock it into a temporarily stable orbit within this sweet spot. These periods of habitability could be fleeting, lasting only a few thousand years before the system's mechanics shift again, and the planet is plunged into a deep freeze or a fiery inferno. For life to arise and persist, it would need to be incredibly resilient, perhaps existing in dormant states for eons before briefly flourishing during these cosmic summers, a testament to tenacity in the face of overwhelming orbital chaos. The search for such environments forces us to expand our imagination of what life could be and where we might eventually find it, pushing the boundaries of the habitable zone from a simple concept into a dynamic and ever-changing puzzle. If the chaotic spin of stars and the wild climate shifts of potential planets push the boundaries of known physics, then the next discovery takes us into a realm that is entirely invisible, detectable only by the most sensitive instruments ever built. We are now listening to the very fabric of space-time itself, and in these sextuple systems, it is singing a song that is far more complex than any theory predicted. The incredible orbital dances of these six massive stars do not just create a light show. They ripple the cosmos, generating gravitational waves, subtle undulations in space-time that propagate outward at the speed of light. For binary systems, the gravitational wave signature is a pure, steady hum, a single tone that slowly increases in pitch and volume as the stars spiral inward. But in a sextuple system, that simple hum transforms into a rich, chaotic symphony. The multitude of overlapping orbital frequencies, the tight whirl of the inner binaries, the slower dance of the quadruple core, and the grand, stately waltz of the outermost pair, all interact, creating a spectrum of gravitational waves with intricate beat patterns, harmonic resonances, and interference effects that are utterly unique. This bizarre and complex waveform is more than just a curiosity. It is a potential Rosetta Stone for testing the limits of Einstein's theory of general relativity under conditions of unimaginable severity. The theory has passed every test we've thrown at it with flying colors, but those tests have largely been in relatively calm gravitational environments, like the space around our sun or the in-spiral of two black holes. A sextuple system is the exact opposite of calm. It is a gravitational maelstrom, a natural laboratory of extreme gravity where the fields are strong, the velocities are high, and the interactions are endlessly complex. The specific way these multiple wave frequencies mix and interfere could reveal subtle discrepancies between the predictions of general relativity and what is actually happening. A tiny deviation in the signal could be the first hint of new physics, perhaps a sign that our understanding of gravity needs to be tweaked or even completely overhauled in such extreme multi-body environments. Furthermore, these unique gravitational wave signatures could act as a powerful new tool for discovery within the systems themselves. The beat patterns and resonances are exquisitely sensitive to the precise masses and orbits of every single object involved. By decoding this cosmic symphony, scientists could potentially uncover the presence of hidden compact objects that are completely invisible to telescopes. The gravitational wave signal might reveal the subtle tug of a stellar mass black hole or a neutron star orbiting within one of the binary pairs, its fierce gravity subtly altering the harmonic pattern of the waves being emitted. It could even provide evidence for the existence of those mysterious retrograde orbits or the captured interstellar immigrants, their presence encoded in the intricate rhythms of spacetime itself. By listening to the gravitational waves of these systems, we are not just observing them from a distance. We are feeling the very distortions their motions create in the universe, offering a profound and entirely new way to understand the most chaotic and magnificent families of stars in the cosmos. And now we arrive at a discovery that challenges one of the most well-established processes in all of stellar astrophysics, the transfer of mass between stars. In a typical binary system, mass transfer is a relatively straightforward, if dramatic, affair. When one star swells into a red giant, it can fill its Roche lobe, a teardrop-shaped region of space where its own gravity is the dominant force. Once this lobe is full, material can spill over the gravitational watershed and onto its companion star, flowing through a point of balance between the two gravitational pulls. This is a well-understood dance between two partners, but in one particular sextuple system, astronomers have observed the unmistakable signature of mass transfer occurring on a cosmic scale they never thought possible. Material is seemingly flowing between stars that aren't even directly paired together. It's as if a channel of stellar gas is leaping across the void, bypassing closer partners to feed a more distant star, defying every model of how this process should work. This observation turns the concept of Roche lobe overflow on its head. The Roche lobe is defined by the gravitational balance between two immediate neighbors. For mass to transfer to a star in a completely different binary pair, separated by billions of kilometers, the entire idea of a localized gravitational watershed must be reconceived. It suggests that the combined gravitational field of all 6 stars is somehow creating a previously unknown kind of gravitational conduit, a focused channel or pipeline through which material can be siphoned across the system. One theory is that the complex interplay of gravitational forces is warping the effective Roche lobes of the stars, stretching them into long, tendril-like shapes that momentarily brush against the lobes of other, non-partner stars during specific phases of their grand orbital dance. Alternatively, the material being ejected from one star, perhaps in a stellar wind, could be being captured and focused by the system's overall gravity, funneling it toward a specific point like light through a lens. The implications of this bizarre phenomenon are tremendous. It means that the chemical enrichment of stars, which elements they contain and in what abundance, is not just a story of their birth cloud or a single binary partner. In these complex systems, a star's composition could be influenced by material donated from a distant cousin, a stellar relative it only encounters once every few thousand years in its orbit. This provides a potential explanation for those strange chemical anomalies we discussed earlier. A star could be enriched with specific heavy elements not from its own evolution, but from a generous and unexpected gift from across the system. This rewrites the rules of stellar evolution itself. The life path of a star, how long it lives, what it becomes when it dies, is dictated by its mass. If a star can gain or lose significant mass through these long-distance transfers, its entire fate is altered. A star destined to end as a quiet white dwarf might instead gather enough mass to explode as a supernova, all because of a constant, gentle rain of material from a distant sibling it never directly touches. This discovery forces astrophysicists to consider that mass transfer is not always a simple, intimate affair between two stars. In the crowded gravitational metropolis of a sextuple system, it can be a communal process, a complex web of exchange that connects all the members in ways we are only beginning to map. It suggests that our models, built on the quiet interactions of isolated pairs, are far too simplistic to capture the dynamic and interconnected life of a true stellar family. After mapping the intricate gravitational waves and uncovering the secrets of mass transfer, we now turn to a more fundamental measurement, one that tracks the very motion of these systems through the galaxy. For centuries, astronomers have charted the paths of stars across the sky, a slow drift known as proper motion. It's the celestial equivalent of watching a ship slowly move across the horizon. With modern telescopes like Gaia, we can measure this motion with breathtaking precision, tracking the exact trajectory of a star system over years and decades. For most stars, this path is a clean, predictable straight line or a gentle arc dictated by the pull of the galaxy as a whole. But for several sextuple systems, the data reveals a persistent and puzzling anomaly. Their path through space is ever so slightly wrong. They are drifting off course, exhibiting a tiny but consistent deviation from their expected trajectory. It's as if these colossal families of stars are being gently tugged by an invisible hand, a force that our current inventory of 6 stars simply cannot account for. This deviation is a classic clue in the astrophysical detective playbook, and it points unequivocally to the presence of additional mass somewhere within or very near the system. The simplest explanation is that we have missed something, that within this already dizzyingly complex family, there are even more members hiding in the shadows. The prime suspects are dark, massive objects that have eluded detection. This could be a brown dwarf, a failed star too dim to see, orbiting far out in the system's periphery. It could be a neutron star or even a stellar mass black hole, the remnant of a 7th star that lived and died long ago and now trails its silent, massive gravity through the system. The gravitational pull from such an object would be constant, gently shepherding the entire sextuple system on a slightly altered course through the Milky Way. However, the mystery deepens considerably when we consider that the anomalies don't always behave as a single, constant tug. In some systems, the deviation seems to vary or doesn't perfectly align with a simple, unseen point of mass. This has led scientists to a far more radical and thrilling possibility, that we are not just seeing hidden stellar objects, but are instead witnessing the gravitational fingerprint of dark matter itself. We know dark matter exists in vast, diffuse halos around galaxies, but could it also clump on smaller scales? The hypothesis is that these incredibly massive sextuple systems could be acting like gravitational magnets, gathering and holding onto a local concentration of dark matter, a dense knot of this mysterious substance that is exerting its own additional pull on the stars. Proving this would be a watershed moment, offering a rare, nearby laboratory to study the properties of dark matter directly. Yet there is a third, equally compelling explanation that looks outward, not inward. Perhaps the anomaly is not caused by something within the system, but by how the system interacts with the galaxy around it. The space between stars is not perfectly empty. It is filled with the tenuous interstellar medium clouds of gas and dust, and crisscrossed by the gravitational fields of other passing star systems. A sextuple system, with its immense combined gravity, might interact with this environment in unique ways. It could be plowing through a particularly dense but invisible cloud of molecular gas, the cumulative drag of all that material subtly breaking its motion. Or the system's path might have taken it close enough to another star or a massive interstellar object to receive a gravitational nudge, a gentle course correction from a distant encounter that happened millennia ago and whose source we can no longer identify. This would mean the anomaly is not a property of the system itself, but a historical record of its journey through the busy galactic neighborhood, a scar from a past collision we never witnessed. The proper motion anomalies are a humbling reminder that for all we have learned about these incredible systems, our map is still incomplete. Whether the culprit is a hidden black hole, a clump of dark matter, or an encounter with the ghostly fabric of the galaxy, these tiny deviations in course are giant signals that there is still much to discover. They represent the frontier of our knowledge, where the known physics of six-body orbits meets the unknown influence of the dark and the distant, pushing us to look deeper and think broader about the true nature of our complex universe. The Sun's heartbeat is a familiar rhythm, an 11-year cycle of rising and falling magnetic activity that dictates the number of sunspots on its surface and the intensity of solar flares. We've long assumed this magnetic pulse was an internal affair, a process governed by the complex dynamo deep within each star's own interior. But in the depths of certain sextuple systems, astronomers have found this rhythm has become a shared experience. Stars separated by trillions of kilometers, members of entirely different binary pairs, are somehow synchronizing their chromospheric activity cycles. Their magnetic personalities are aligning, their stellar spots and flares rising and falling in concert, as if connected by an invisible conductor ensuring the entire cosmic orchestra plays the same magnetic symphony. This synchronization is one of the most baffling discoveries yet because the mechanism behind a star's magnetic cycle is incredibly complex and fundamentally local. It's driven by the star's own internal rotation and the churning motions of plasma in its convective zone, a process that should be completely independent from its distant stellar siblings. For these cycles to lock in step across such vast distances suggests a form of communication that transcends the empty space between them, a way for one star's internal dynamo to influence another's. The sheer scale of this coordination makes it clear that the complex gravitational web of a sextuple system is doing far more than just dictating orbits. It is somehow fine-tuning the most fundamental energetic processes within the stars themselves. Scientists are investigating two primary and equally extraordinary mechanisms that could be behind this interstellar synchronicity. The first revolves around the subtle, rhythmic tug of gravity. As the stars complete their intricate orbital dance, the gravitational forces they exert on each other change in a precise, periodic pattern. These tiny tidal forces could act like a persistent, gentle massage on a star's outer layers. This gravitational kneading might be enough to influence the flow of plasma in the star's convective zone, the very region where its magnetic field is generated. Over time, these rhythmic gravitational nudges could entrain the internal dynamo, slowly forcing it to sync its cycle with the orbital period of its most influential neighbor. It would be an incredible demonstration of gravity's reach, proving it can regulate not just a star's path, but its very internal energy. The second possibility involves the system's shared environment. The space between these stars is not a perfect vacuum. It is filled with stellar winds, radiation, and magnetic fields. One theory suggests that the powerful magnetic field of the most active star in the system could be acting as a pacemaker. As this field sweeps through the system, it could modulate the flow of the interstellar medium, creating a rhythmic pressure that impacts the magnetospheres of the other stars. Alternatively, the intense and periodic ultraviolet radiation from a hot, variable star could heat the outer atmospheres of its companions, altering their ionization levels and thereby influencing the conditions for magnetic field generation. In this scenario, the stars aren't communicating through force, but through light and energy, their cycles locked together by the shared sea of radiation they all swim within. The implications of this discovery stretch far beyond a simple curiosity. If true, it means we can no longer study a star's magnetic life in isolation. Its personality, its activity cycle, and even its potential for nurturing life on orbiting planets might be profoundly shaped by its stellar family. A star's magnetic mood swings drive space weather, the stellar flares and radiation storms that can sterilize planets or strip away their atmospheres. In a synchronized system, these potentially deadly events wouldn't be random. They could occur in system-wide storms, periods where all stars flare up in unison, bathing every planet in the family in a simultaneous barrage of high-energy radiation. This redefines our search for habitable worlds, suggesting that true, long-term stability might require a star to be not just the right size and temperature, but to also have the right kind of family, one that keeps its magnetic rhythms calm and predictable, rather than locked into a chaotic, system-wide tantrum. While we've been captivated by the individual oddities of these stellar families, from their synchronized pulses to their rebellious spins, stepping back to look at them as a population reveals a pattern so strange it points to a fundamental difference in their very creation. Astronomers have now compiled data on numerous sextuple systems and performed a deep statistical analysis, comparing the properties of their binary pairs to the vast catalog of isolated binaries that fill the galaxy. The expectation was simple: the building blocks should look the same. Whether a binary is alone or part of a larger family, the process of two stars forming from a single cloud should follow the same physical rules, resulting in similar distributions of mass ratios, how the mass of one star compares to its partner, and separation distances. But the data tells a completely different story. The binaries inside sextuple systems are not like the others. They follow a distinct and unexpected set of rules, a hidden signature that suggests their formation was anything but ordinary. In the wider galaxy, isolated binary pairs show a fascinating preference. There's a well-documented tendency for stars of similar mass to partner up. It's far more common to find a binary where the two stars are twins with a mass ratio close to 1 than it is to find a pairing between a heavyweight and a lightweight. The distribution of their separations is also broad and varied, with no strong preference for any specific distance. But within the complex gravitational web of a sextuple system, this galactic trend is turned on its head. The analysis reveals a surprising abundance of what astronomers call extreme mass ratio binaries. These are pairs where one star is significantly more massive than the other, a partnership of a giant and a dwarf. Furthermore, the distances between these paired stars are not random. They seem to be funneled into two preferred categories, either extremely tight orbits where the stars whirl around each other in a matter of days, or very wide orbits where their dance is slow and stately. The middle ground, the moderate separations that are common elsewhere, appears to be conspicuously missing from the sextuple family album. This bizarre statistical skew is a massive clue, and it forces a dramatic rethinking of how these systems are built. It strongly suggests that the individual binary pairs did not form in peaceful isolation before somehow finding each other. If that were the case, their properties would mirror the broader population. Instead, this unique distribution screams that the entire system, all 6 stars, was born together in a single, extraordinarily dynamic and interactive event. The formation of one pair must have directly influenced the formation of the others, imposing constraints and triggering mechanisms that don't exist for a simple binary alone. The prevalence of tight binaries, for instance, hints at a violent birth cloud that was unusually efficient at dissipating angular momentum, allowing stars to spiral very close together without merging. The excess of extreme mass ratios could be a direct result of this crowded nursery. Perhaps the gravitational pull from other forming stars nearby literally stole material from one protostar and fed it to its partner, creating a lopsided pair. This isn't just a minor statistical curiosity, it's a foundational insight. It means that the physics governing the creation of a sextuple star system is a distinct branch of astrophysics, separate from the processes that make solitary stars or simple binaries. The chaos of a six-star nursery imposes its own unique set of rules, favoring certain outcomes and suppressing others. By decoding this hidden pattern in the ratios and distances, we are essentially reading the blueprints from the construction site of these cosmic families, blueprints that reveal a far more violent, competitive, and interconnected origin story than we ever imagined. While the gravitational complexities within these systems are staggering, their influence does not stop at the boundaries of their own orbits. These stellar families are not isolated islands. They are massive ships sailing through the ocean of space, and their journey leaves a wake that is far more elaborate than anything a single star could produce. As a sextuple system moves through the galaxy, it plows through the thin gas and dust of the interstellar medium. A single star, like our Sun, creates a simple bow shock, a gentle arc of compressed material, similar to the wave at the prow of a boat. But a system with 6 stars, each a powerful source of radiation and stellar wind, and all of them moving in a complex gravitational dance, creates an interstellar interaction of breathtaking complexity. The resulting structure is not a single, clean arc. Instead, it's a chaotic, layered tapestry of multiple bow shocks, turbulent wakes, and overlapping cavities, all shaped by the competing influences of the different stellar members. The strangeness of this structure comes from the fact that the system doesn't present a single, unified face to the interstellar medium. Imagine 6 different lighthouses on a single, moving island, each spinning at a different speed and shining with a different colored light. The radiation pressure and stellar winds from each star push against the interstellar gas, but they do so from constantly shifting positions within the system. The hottest, most massive blue giant might be leading the charge at one moment, its fierce ultraviolet radiation ionizing and blowing a huge bubble ahead of the pack. Meanwhile, a cooler red dwarf in a different part of its orbit might be trailing behind, its weaker wind creating a smaller, more subdued shock wave. As the stars continue their dance, these individual structures collide, merge, and tear apart, creating a permanently changing and incredibly intricate pattern of compressed gas and heated plasma that telescopes can detect in brilliant infrared and radio wavelengths. This bizarre interaction does more than just create a beautiful cosmic light show. It may actively seed new processes in its wake. The complex pattern of shocks and compressions acts like a series of cosmic plows and tampers, pushing the tenuous interstellar material into dense, rippled sheets and knots. In certain regions, this forced compression could be the trigger that pushes a stable cloud of gas over the edge of its own gravity, initiating the collapse that leads to the birth of entirely new stars. This means a sextuple system could be a traveling factory of creation, leaving a trail of potential stellar nurseries in its path. The composition of these new stars would also be unusual, forged from material that has been processed through the violent shocks and irradiated by the intense light of 6 different suns, potentially enriching them with specific elements in a way that wouldn't occur in a quieter region of space. The idea that these most chaotic of systems could be responsible for fostering the birth of others adds a profound new layer to their role in the galactic ecosystem, painting them not as destructive anomalies but as unlikely and magnificent agents of change. Beyond the intricate gravitational choreography and the symphony of synchronized pulses lies a profound challenge that strikes at the very heart of our ability to predict the cosmos, the temporal evolution puzzle. When astrophysicists attempt to simulate the life story of a sextuple star system on a supercomputer, they are immediately confronted with a wall of pure mathematical chaos. The equations governing the motion of 6 massive bodies are so exquisitely sensitive that changing the starting position of a single star by a mere few thousand kilometers, a trivial distance on the cosmic scale, can lead to a completely different fate for the entire system. In one simulation, the arrangement might remain stable for billions of years, a perfect hierarchical dance. In another, almost identical run, the same system might violently eject two stars into interstellar space after just a few million years or trigger a cataclysmic collision. This extreme sensitivity is a fundamental property of complex gravitational systems, a phenomenon famously known as the butterfly effect, where the flapping of a butterfly's wings could theoretically influence the path of a hurricane. According to our best models, this inherent chaos should make long-lived sextuple systems incredibly rare, fleeting accidents in the galaxy. Yet when we look up at the real universe, we find the exact opposite. We observe ancient sextuple systems, their rhythms apparently undisturbed for timescales longer than the age of Earth itself. They are not rare, fleeting accidents, they are enduring cosmic institutions. This glaring contradiction between what the simulations predict and what we actually observe creates a baffling sensitivity paradox. The universe seems to possess a hidden recipe for stability that our most powerful computers and sophisticated equations have not yet managed to decode. It forces us to ask a humbling question. Are our models missing a key ingredient, or are we fundamentally misunderstanding how these systems are born? One compelling resolution to this paradox is that we simply haven't identified all the subtle stabilizing mechanisms at play. Our simulations might account for gravity, but they could be overlooking other physical forces that act as cosmic shock absorbers. For instance, the gravitational influence of those vast circumstellar disks of gas and dust could provide a stabilizing drag, gently damping orbital oscillations that would otherwise grow out of control. Alternatively, the complex magnetic interactions between stars could transfer energy in a way that helps to maintain equilibrium, much like gyroscopes stabilizing a satellite. It's also possible that the general relativistic effects, which are minuscule but persistent, play a more significant role in these extreme environments than we've assumed, providing a subtle framework that prevents the Newtonian chaos from taking over. The other, more profound possibility is that the formation process itself is the key. Our simulations typically start with 6 fully formed stars placed in arbitrary orbits, but nature doesn't work that way. These systems are not assembled from random parts, they are born together from a single, collapsing cloud. This shared origin might inherently produce them in exceptionally stable configurations. The turbulence and magnetic fields within the birth cloud could naturally funnel the emerging stars into orbits that are already pre-tuned for longevity, locked into deep gravitational resonances from their very first moments. In this view, the stable systems we see are not the lucky survivors of a chaotic process, they are the only possible outcome. The formation mechanism acts as a cosmic filter, ensuring that only the most robust and finely balanced architectures ever come into existence in the first place. The chaotic systems our simulations produce may simply never form at all, weeded out by physics during the birthing process itself. This idea suggests that to truly understand the life of a sextuple system, we must first fully understand its extraordinarily precise and delicate birth. As we've seen, the gravitational dynamics and magnetic symphonies of these systems are complex, but perhaps the most subtle and perplexing clues are written in the very light they emit. When astronomers break down this light into its constituent colors using a spectrograph, they expect to see a predictable pattern, a series of dark absorption lines at specific wavelengths, like a barcode identifying the elements present in each star's atmosphere. As the stars orbit, the Doppler shift should cause these lines to rhythmically wobble blueward and redward, telling us precisely about their motion. But in several sextuple systems, this elegant picture falls apart. The spectral lines themselves are behaving strangely, showing variations in their shape, depth, and position that cannot be explained by simple orbital dynamics alone. It's as if the stellar barcode is smudged, flickering, and shifting in ways that defy our standard models. hinting at a layer of physics operating within and between these stars that we have never before had to consider. These spectral anomalies present a fascinating puzzle because they point to processes that are altering the light after it leaves the star's photosphere, but before it travels across the interstellar void to our telescopes. One compelling explanation involves complex atmospheric interactions on a scale we can barely imagine. In a tight binary pair, the stars are so close that their extended atmospheres or chromospheres could actually be interacting. The fierce stellar winds and powerful magnetic fields from one star might be constantly buffeting the atmosphere of its partner, heating it, stripping material away, or creating standing shock waves that alter the density and temperature of the gas. This would cause the absorption lines formed in that agitated region to weaken, strengthen, or shift in unpredictable ways, creating a spectral signature of a star whose outer layers are being perpetually stirred by a violent companion. Another possibility pushes into the realm of exotic stellar pulsations. We are familiar with variable stars that rhythmically expand and contract, but the extreme gravitational environment of a sextuple system could be driving entirely new and unknown modes of vibration. The persistent tidal pulls from multiple stars could be exciting subtle, high-frequency pulsations that ripple across a star's surface. These wouldn't be the large-scale brightness changes we typically associate with variable stars, but more delicate oscillations that primarily affect the specific wavelengths of light absorbed at the surface. This would cause the spectral lines to appear to breathe, widening and narrowing, or developing strange asymmetries as the pulsating surface alters the conditions under which the light is absorbed. Detecting this would be like seismology for distant suns, using the tiny tremors in their light to map the internal structure of stars being played like instruments by their gravitational orchestra. Perhaps the most mind-bending theory involves the subtle warping of spacetime itself. General relativity tells us that gravity can bend light, a phenomenon known as gravitational lensing. We typically observe this on a colossal scale, with massive galaxy clusters lensing the light from objects behind them. But within a sextuple system, the same principle could be at work on a smaller, more intricate scale. As light from one star travels past its 5 siblings on its way to us, the combined gravitational field of the entire system could act as a complex lens, minutely deflecting the light rays and very slightly altering their path. This wouldn't create multiple images like a strong lens, but it could subtly smear and distort the spectral lines, making them appear to shift in a way that mimics velocity, but is actually a trick of gravity. It would be an incredibly subtle effect, but in these precise spectroscopic measurements, it might just be detectable. If confirmed, it would mean we are not just observing the stars, but also seeing the ghostly imprint of their collective gravity written directly onto their light, a tiny whisper of Einstein's theory playing out in the confines of a single stellar family. Just when we thought the stellar demographics of these systems couldn't get any stranger, we encounter a discovery that reads like a cosmic census report from another reality. Astronomers have long categorized stars into broad population groups based on their chemical makeup. Population 1 stars, like our Sun, are metal-rich, born from gas that has been cycled through multiple generations of stellar furnaces. Population 2 stars are ancient relics, metal-poor veterans from the early universe. These groups tell the story of galactic evolution, with older stars generally found in different regions than younger ones. But in at least one known sextuple system, this tidy historical narrative completely collapses. Here, astronomers have identified stars from these vastly different populations living side by side as gravitational siblings. It's the equivalent of an archaeological dig finding a smartphone buried next to a stone axe in the same layer of Earth, a violation of the natural chronological order that forces a complete rethink of how this family came to be. The presence of both extreme population I and population Roman II stars in a single, bound system is a profound contradiction. A metal-rich young star simply does not form in the same environment or at the same time as an ancient metal-poor star. Their chemical compositions are a direct record of the conditions in the galactic gas cloud from which they condensed. A high metallicity indicates a birth cloud enriched by countless supernovae, a sign of a busy, evolved galactic region. A low metallicity points to a pristine, early universe environment. For these stars to be locked in a gravitational embrace means their origin stories must be wildly different, yet their fates became inextricably linked. This demographic impossibility points to a history far more dramatic than a quiet, co-formative birth. The most compelling explanation for this bizarre stellar genealogy is a history of interstellar capture on a grand scale. This system may not be a family by birth, but a family by adoption, assembled over billions of years through a series of incredibly unlikely gravitational encounters. Imagine the system beginning its life as a small, ancient cluster of population Roman II stars formed together in the galaxy's youth. Over eons, as it drifted through the Milky Way, its path may have crossed that of a much younger, metal-rich binary pair. Through a complex gravitational dance, perhaps a gentle gravitational brake applied by a passing molecular cloud or a precise three-body interaction, the younger system could have been captured, its velocity slowed just enough to become bound to the older family. This would create a blended stellar household, with members bearing the chemical signatures of completely different eras and locations in the galaxy. Alternatively, the system itself could be the product of a galactic merger event. Our Milky Way is growing by absorbing smaller dwarf galaxies, which often contain older, metal-poor stars. It's possible this entire sextuple system was once the core of such a small galaxy that was cannibalized by the Milky Way. During this violent process, the gravitational tides could have funneled in new, metal-rich gas from the larger galaxy, which then collapsed to form a new generation of population-I stars right there amidst the ancient population. This would mean the system itself is a microcosm of galactic evolution, a miniature version of the entire Milky Way's history contained within 6 gravitationally linked stars. The very existence of such a system challenges the clean division between stellar populations and suggests that the galaxy's history is written not just in broad trends, but in the intricate and chaotic family trees of its most complex stellar systems. While we have been listening to the gravitational waves and reading the spectral fingerprints of these stellar families, another part of the electromagnetic spectrum is telling its own bizarre story. In the quiet, long-wavelength realm of radio astronomy, several sextuple systems are anything but silent. They are broadcasting powerful, fluctuating signals that crackle with an energy that defies all classification. These are not the predictable, periodic pulses of a spinning neutron star, nor the violent, short-lived static burst of a stellar flare. This radio emission is something entirely new, a strong, variable, and enigmatic radio voice with no known counterpart in our celestial catalog, suggesting that within these complex systems, nature has invented a novel way to make stars shout across the cosmos. The mystery lies in the complete disconnect between the signal and any conceivable source. When a star produces radio waves, it's usually through a process we understand. Flare stars, for instance, generate radio bursts through massive magnetic explosions in their corona. Pulsars create their lighthouse like beams through the precise funneling of radiation from their magnetic poles. But in these systems, the radio signatures match none of these profiles. The emission is too persistent and structured to be random flare noise, yet too chaotic and variable to be the clean clockwork of a pulsar. Furthermore, the strength of the signal is often disproportionate to the types of stars present. Quieter, calmer stars are producing radio noise that would be more typical of a truly monstrous stellar outburst. This forces astronomers to confront a thrilling possibility that the radio emission is not generated by any single star, but is instead a collective phenomenon, a product of the system's complex environment that simply cannot exist around a solitary sun. A primary theory points to a previously unimagined scale of plasma interaction. Each star in these systems is blowing out a constant stream of charged particles, its stellar wind. In a sextuple system, these 6 winds do not travel peacefully into the void, they collide. Imagine 6 hurricane-force winds meeting in a cosmic intersection, with each gust carrying its own magnetic field. When these magnetized plasmas slam into each other at velocities that are a significant fraction of the speed of light, the result is chaos on an atomic scale. The collisions can generate immense shock waves that accelerate electrons to nearly light speed. When these ultra-relativistic electrons are then caught in the tangled web of magnetic fields, they spiral wildly, emitting synchrotron radiation, a powerful and broad spectrum of radio waves. The variability of the signal could then be dictated by the orbital dance itself, as the changing positions of the stars cause their winds to collide at different angles and intensities, essentially tuning a colossal natural radio transmitter. A second, more exotic hypothesis involves coherent emission processes. Most astronomical radio sources are incoherent, meaning the particles emitting the radiation are doing so independently, like a crowd of people all talking at once. But the signals from some of these systems have a sharpness and intensity that hint at coherence, a scenario where particles act in concert, like a laser but for radio waves. This requires a very specific and rare set of conditions to naturally amplify the radio waves. One proposed mechanism is a maser effect, where energy is pumped into a cloud of molecules, like water or hydroxyl, causing them to emit radio waves in a synchronized, amplified beam. The complex environment of a sextuple system, with its multiple sources of intense radiation and shock fronts, could be creating the perfect conditions for powerful natural masers to form at an unprecedented scale, turning entire regions of space between the stars into giant, focused radio amplifiers. Perhaps the most intriguing possibility, however, involves unseen planets. We have discussed the potential for worlds in these systems, and their magnetospheres could be key players. A planet with a strong magnetic field, like a super-sized Jupiter, orbiting within the brutal environment of a sextuple system, would be subjected to an onslaught of charged particles from multiple stellar winds. Its magnetosphere would be constantly buffeted and compressed, a process that, in our own solar system, generates intense radio emission from Jupiter itself. Now amplify that scenario by a factor of 100. A planet in a sextuple system would be caught in a perpetual storm of intersecting winds, its magnetosphere becoming a continuous generator of radio static as it processes this chaotic influx of energy. The varying signal we detect could be the planet's magnetic field screaming under the strain, its radio voice modulated by its orbit through the ever-changing stellar environment. This would mean the mysterious radio signature is not a cry from the stars themselves, but an amplified distress call from a hidden world, a planet struggling to maintain its magnetic shield in the most tumultuous neighborhood in the galaxy. But perhaps the most surprising astroseismological discovery involves the very heartbeat of stellar fusion itself. In certain component stars, the oscillation patterns indicate abnormal temperatures and densities in their cores, suggesting that nuclear burning rates are proceeding at a pace that contradicts established models for stars of their mass. A star that should be calmly fusing hydrogen might show signs of operating at a more frantic, intensified rate, while another that should be more active appears strangely subdued. This points to the gravitational environment itself acting as a regulator of stellar energy production. The constant, rhythmic tidal squeezing from nearby companions could be literally stirring the pot in these stellar cores, enhancing mixing and bringing fresh fuel to the fusion furnace, thereby altering the star's fundamental energy output and potentially shortening or extending its lifespan in ways we never anticipated. These stars are not living their lives in isolation according to a predictable clock. Their internal fires are being stoked or banked by the gravitational hands of their family members. After probing the depths of their nuclear hearts and listening to their chaotic radio voices, we turn our attention to the very dust from which these systems were born. In the quiet spaces between these 6 dancing stars, astronomers have trained their most sensitive instruments on the clouds of dust and debris, expecting to find a familiar composition, a mix of silicates, carbon grains, and ices similar to what we see around single stars or simpler binaries. Instead, the spectral fingerprints reveal a profound anomaly. The dust itself is different. It's not just the same cosmic ingredients in new proportions. It's as if the very recipe for dust has been rewritten, producing mineralogical structures and chemical patterns that defy all expectations and have no clear counterpart anywhere else in the galaxy. This isn't a matter of a little more of one element and a little less of another. The dust grains show evidence of highly unusual crystal structures. Certain silicate compounds, which around a typical star might form in messy, amorphous blobs, here appear to have been annealed into perfectly ordered crystalline lattices, as if fired in a cosmic kiln. There are also perplexing abundance patterns of heavy elements like iron, nickel, and even precious metals like gold and platinum, which appear to be heavily enriched or depleted in the dust compared to the gas phase. In some cases, these metals seem to have been literally plated onto the surfaces of dust grains, creating strange, metallic-coated sand that shimmers in the starlight. This isn't the primordial, unprocessed dust of a typical stellar nursery. This is dust that has been radically altered, processed by forces we are only beginning to understand. The central mystery is whether this bizarre dust is a product of the system's violent present or a relic of its unique birth. The first theory points to the extreme environment as a colossal processing plant. With 6 stars, the radiation field is incredibly complex and intense. A dust grain orbiting within the system isn't just gently warmed by a single source of light. It is bombarded by ultraviolet radiation from a hot blue giant, infrared from a cool red dwarf, and the fierce stellar winds from all of them, each from constantly shifting directions. This multidirectional assault could be literally sandblasting and annealing the grains, blasting off volatile ices and gently heating the more refractory minerals, allowing them to reorganize into those perfect crystalline structures. Furthermore, the powerful shock waves generated as these stellar winds collide at incredible speeds could be acting like immense natural forges, compressing and heating pockets of dust and gas to temperatures high enough to vaporize and recondense the grains into these new, exotic forms. In this scenario, the system is a continuous refinery, taking ordinary cosmic dust and processing it into something entirely new. The alternative explanation is even more radical, that this strange dust is a fossil, a preserved sample of the system's initial conditions. Perhaps this sextuple system didn't form from a standard, well-mixed cloud of gas and dust. Instead, it may have coalesced from a cloud that was already pre-enriched and chemically distinct, perhaps the remnant of a nearby supernova explosion that seeded the nursery with an unusual mix of heavy elements and radioactive isotopes. The heat from these radioactive elements in the system's earliest days could have baked the dust from within, altering its composition before the stars even finished forming. This would mean the anomalous dust isn't a product of the system's complexity, but rather the very reason for it, the unique chemical makeup of the birth cloud, might have been what allowed 6 stars to form so close together in the first place, with the dust acting as a cooling agent or a catalyst for fragmentation in a way that normal dust could not. Unraveling this mystery is about more than just cataloging strange rocks in space. It strikes at the core of how planets are built. Planets form from this dust. If the fundamental building blocks are different, then the planets that coalesce from them will be different too. A world formed from metallic-coated, crystalline silicate dust would have a radically different geology, surface chemistry, and perhaps even a different potential for chemistry that could lead to life, compared to a planet formed from the primordial dust of a quieter system. The dust composition anomalies force us to realize that the path from stardust to planets is not a single, universal road. In the chaotic gravitational metropolises of sextuple star systems, the universe is following a different set of blueprints, constructing worlds from materials we are only just beginning to recognize. After untangling the chaotic radio signals and the strange chemistry of their dust, we arrive at a discovery that speaks to the very geometry of these systems, a finding so orderly it seems to defy the chaos from which they were born. When you picture a system with 6 stars, you might imagine a three-dimensional hive of activity, with orbits tilted and inclined at every possible angle, a celestial game of pick-up sticks frozen in motion. This is exactly what our standard models of star formation predict. When a large cloud of gas and dust collapses, it fragments, and those fragments should spin up with random orientations, their orbital planes scattered like pages from a book dropped haphazardly on the floor. But when astronomers meticulously mapped the orbital inclinations of the binary pairs in several sextuple systems, they found something profoundly different. The orbits weren't random. The planes of these separate dances were far more closely aligned than mere chance could possibly allow. It's as if the entire system, for all its complex motion, was somehow flattened during its birth, its components choosing to dance on a common stage rather than in a free-for-all. This proper alignment is a massive clue, a silent signal from the system's earliest moments that challenges the notion of a purely chaotic gravitational collapse. If the orbits were random, it would suggest that each binary pair formed from its own isolated knot of turbulence within the cloud, with no memory of its siblings. The fact that they are aligned means that the entire system retained a sense of order, a collective memory of a shared spin axis that persisted even as the cloud broke apart. This points to a formation process that was far more coordinated than we ever imagined. The leading theory to explain this involves the ghostly hand of magnetic fields. In the system's primordial cloud, powerful magnetic field lines would have acted like invisible threads weaving through the gas. As the cloud began to collapse, these field lines would have resisted any motion that tried to pull material across them, effectively channeling the collapse and enforcing a preferred direction of rotation. This magnetic braking would have forced the entire system, even as it fragmented into multiple stars, to conserve that original spin, leaving all the resulting orbits aligned like dancers all turning on the same axis. A second compelling force is the influence of the very disk from which the stars were born. We now believe that most stars form not from a shapeless cloud, but within a flattened, spinning protostellar disk. In a simple system, a single star forms from the center of that disk, but in a massive cloud destined to become a sextuple system, the disk itself might have been vast, and the fragmentation process could have happened within that disk. If all 6 stars began their lives as over-dense regions within a single, gigantic disk, then they would all naturally inherit the same orbital plane, the plane of the disk itself. Their orbits would be aligned because they were all born from the same cosmic frisbee, their paths imprinted by its rotation long before they finally ignited and cleared their immediate surroundings. This discovery of non-random alignment is more than just a curiosity. It's a powerful constraint, a set of blueprints that tells us which formation theories are plausible and which must be discarded. It suggests that for all their eventual complexity, these stellar families began their lives with a surprising degree of cosmic order. The final and perhaps most mind-expanding discovery in our journey through these stellar families forces us to completely reimagine the very idea of a habitable world. We are accustomed to the comforting simplicity of a single star's habitable zone, that narrow, circular band where temperatures are just right for liquid water to exist on a planet's surface. But in a sextuple system, this simple, elegant concept shatters into a breathtakingly complex and dynamic three-dimensional puzzle. A planet here isn't orbiting one sun. It is navigating a gravitational and radiative maze with up to 6 different sources of light and heat, each with its own unique color, intensity, and orbital rhythm. The combined energy bathing this world doesn't come from a single, constant point. It's a symphony of fluctuating stellar influences, creating a climate and light environment so bizarre it challenges our very definition of what life could endure. The true strangeness lies in the paradox that this apparent chaos might actually be a source of stability. Around a single star like our Sun, a planet's climate is vulnerable to the star's own mood swings. A period of intense solar activity can trigger warming, while a prolonged quiet spell might nudge a world toward an ice age. But in a sextuple system, the combined heating from multiple stars could create a powerful averaging effect. Imagine a planet that, for part of its long orbit, receives gentle warmth from a nearby red dwarf. As it moves away, the diminishing heat from that star might be perfectly compensated by its approach toward a more distant but intensely bright blue giant. The planet's temperature, instead of swinging wildly, could be held in a remarkably steady, life-friendly balance by this celestial thermostat, a delicate counterpoint of stellar influences that smooths out the extremes. In this scenario, the greatest threat to life isn't temperature variation, but rather the immense gravitational chaos that could destabilize the planet's orbit and break this delicate balancing act. Conversely, these systems could also produce environments of such exotic extremity that they force us to expand the boundaries of biological possibility. Picture a world where the concept of day and night loses all meaning, with multiple suns of different colors constantly rising and setting in a complex, unpredictable ballet. The sky might never be fully dark. The primary light for photosynthesis could shift from the familiar white-yellow of our sun to the deep red of a dwarf star, forcing plant life to adapt by using completely different pigments, perhaps appearing black to absorb every available photon. The ultraviolet radiation baths from a close blue giant could be lethal, meaning any surface life would need to be subterranean or aquatic, only emerging during the brief, golden hours when the protective light of a cooler star dominates the sky. A year wouldn't be a simple cycle of seasons. It would be a chaotic calendar of stellar proximities, with epochs of endless daylight under multiple suns followed by periods of dim, twilight gloom under a single, faint star. This redefines the entire astrobiological search. We can no longer simply look for a planet sitting in a single star's habitable zone. We must now search for gravitational sweet spots within these complex systems, temporary or long-lasting orbital configurations where the combined stellar energies from multiple sources overlap to create a stable, temperate volume of space. A planet might only be habitable for a few thousand years at a time before the gravitational dance of its 6 suns moves it out of this sweet spot, meaning life would need to be incredibly resilient, perhaps existing in dormant spore states for eons between brief flowering periods of habitability. The discovery of such a world would be the ultimate testament to life's tenacity, proving that even in the most tumultuous and seemingly hostile environments imaginable, the universe holds onto the potential for existence, rewriting the rules of biology under the light of 6 suns. As we conclude this incredible journey through 30 of the strangest discoveries about sextuple star systems, one overarching truth becomes undeniably clear. These are not merely celestial curiosities, but the universe's most sophisticated natural laboratories. Each finding, from the impossibly stable orbits and synchronized heartbeats to the magnetic symphonies and chemical anomalies, chips away at the foundations of our textbooks, forcing us to rewrite the rules of stellar physics, planetary formation, and gravitational dynamics. We began by looking up at a familiar constellation like Gemini, only to learn that the single point of light we call Castor is an intricate dance of 6 stars, a powerful lesson in cosmic humility that set the stage for everything that followed. We've seen how planets might somehow form in the midst of gravitational chaos, how stars of wildly different ages and compositions can become family, and how the very fabric of space-time ripples with a complex symphony of waves generated by their orbital dance. These systems challenge us to think in multiple dimensions, to consider habitable zones not as simple circles around a single star, but as dynamic, evolving volumes of space where the combined light and heat of 6 suns might, against all odds, create temporary niches where life could persist. They hint at entirely new channels for creating the heavy elements that make up our world, and suggest that the very spin of a star can be dictated by its distant siblings. Perhaps most profoundly, the mere existence of these ancient, stable systems is a paradox that humbles our most powerful supercomputers, suggesting that the universe possesses a hidden recipe for order within complexity that we are only beginning to appreciate. So we leave you with this question to ponder and share. Which of these bizarre findings captured your imagination the most? Was it the stars communicating through magnetic fields across billions of kilometers, the potential for a planet with a 6-sun sunset, or the haunting possibility that orbital anomalies are revealing the fingerprints of dark matter or even new laws of physics? Let us know in the comments below. If unraveling the deepest mysteries of the cosmos fuels your curiosity as much as it does ours, be sure to subscribe and hit the bell so you don't miss our next journey into the unknown. Thank you for joining us on this expedition to the very edge of our understanding, where every answer reveals a dozen new questions and the universe continues to defy our expectations at every turn.